Hi guys, this is another sample video, and this sample video is directed towards college students who may be preparing for IIT JAM and JEST. Again, because this is a sample video, uh, I want to do something that is essentially simple, and originally thought about deriving the Euler-Lagrange equations, but I want to do something that I can contain within a certain amount of time. So I decided upon deriving the Newton's second laws, but from the principle of least action. Uh, the principle of least action is the fundamental principle behind the Euler-Lagrange equations. The actual derivation of the Euler-Lagrange equations is a little more complicated, but the fundamental principle is essentially the same as what I'm going to do here. So let me begin, and let me repeat once again. What I'm going to do is I'm going to derive Newton's second law, but from the principle of least action. So first we need to know what the action is. The action, the classical action, it's denoted by the letter S. It is a functional, it's not a function, it's a functional, and it is defined to be the integration of L dt, L being the Lagrangian. This is a definite integral and the limits are from t1 to t2. The Lagrangian is a function. So the classical action takes a function as its argument and returns a number. Therefore, the action is a functional. What is the Lagrangian? The Lagrangian can be many things. In complicated systems, there can also be restrictions on what the Lagrangian can be. But I'm going to use the entire principle for a single particle in some potential field. For a single particle in some potential field, the Lagrangian is very simple. It's the difference of the kinetic and the potential energies. The Hamiltonian being the sum of the kinetic and potential energies, and therefore being the energy. The Lagrangian is the difference of the kinetic and potential energies. So half m x dot squared, by x dot I mean derivative of x with respect to time, therefore x dot is the velocity, so half mv squared can also be written as half m x dot squared minus the potential energy, where I assume that the potential energy V is a function of position. So here's my Lagrangian, therefore my action is integration from t1 to t2 half mx dot squared minus vx, and the entire thing has to be integrated in time dt. The limits being t1 to t2. Now what does the principle of least action say? It says that, suppose this axis is position and this axis is time, it says that if there is a certain particle in some potential field and you have to determine what path it takes in going from this point to this point between times t1 and t2, the principle of least action basically says that the particle will follow a path which minimizes or makes stationary is the more correct phrase, which makes stationary this quantity. Now, it may not be this path. The correct path can be this, or it can be this. I don't know what the correct path is, but I'm assuming that there is a correct path. What are the total number of paths that the particle can take in going from this point to this point? Well, there are infinitely many paths, but only one of those paths will be the actual path followed by the particle. And which path will that be? Well, it will be the path which makes stationary or minimizes the action. So in going from here to here, there are infinitely many paths, but the correct path, the actual path that is followed, is the one which makes stationary or minimizes this quantity. I do not need this diagram. Well, I do need it. I do need this diagram, but eventually I'm going to erase it because I have very limited space to work with. How do we proceed from here? Well, to proceed, we'll have to assume that there is some correct path, and we are trying to find that correct path, but in our attempts we have missed that correct path by a very small amount. We let that amount be epsilon. So I'm assuming that this is the correct path in my diagram, but this is only a diagram, it's a representation. The correct path may not be this, but whatever it is, in trying to find the correct path, I've missed the correct path by a very small amount, epsilon. So if I have to calculate the action for my path which is not the correct path, for my wrong path, then I will have to let my x go to x plus epsilon. So there is a certain shift of coordinates. In that case, x dot will go to x dot plus epsilon dot. Now I no longer need this diagram. You must assure yourself that all I'm trying to say is that there is a correct path, and for that correct path the action is minimum or stationary, and in trying to find that correct path I've missed that correct path by a very small amount epsilon. Therefore, for my wrong path, x goes to x plus epsilon, and the derivative of x with respect to time, x dot, goes to x dot plus epsilon dot. So there's I'm sorry, there's a certain shift of coordinates. If I erase this diagram now, let me now write down the new action. The new action, S, is again an integral from t1 to t2. X dot now goes to x dot plus epsilon dot. So x dot plus epsilon dot squared minus v. X goes to x plus epsilon. So the potential energy, instead of being a function of x, now it is a function of x plus epsilon. The whole thing has to be integrated in time dt. Well, one thing that I should have mentioned was that in going from here to here, I had assumed that there was some correct path, and I had missed that correct path by an amount epsilon, by a very small amount epsilon. What I should have said also is that in trying to figure out the correct path from here to here, I'm changing the coordinates, I'm changing the values of x, but not at the endpoints. The endpoints are fixed. I can't change the endpoints. The endpoints were given to me in the problem itself. So the endpoints are fixed. All the points that come in between, they can be shifted. So epsilon at t1, t1 being this time, and epsilon at t2, t2 being this time, they are both 0 because the endpoints are not being changed. So there is no variation of position at the endpoints at t1 and t2. We'll also need this. Okay. Since I do not have too much space to work with, I'll try to do it here itself. How can we simplify this? Well, we can expand this. X dot plus epsilon dot squared can be written as x dot squared plus epsilon dot squared plus twice x dot epsilon dot And what can I do with V of x plus epsilon? Well, I can Taylor expand it and I can ignore higher order terms, terms containing higher powers of epsilon. Epsilon being small, its powers will be even smaller. So if we Taylor expand this quantity, erasing this and writing the Taylor expansion in its place, I get Vx plus epsilon dV by dx. This is the curtailed Taylor expansion of V of x plus epsilon. Of course, this is not exactly equal to V of x plus epsilon. For the exact expression, I would have to write down many higher order terms containing higher powers of epsilon. But because epsilon is small, its powers are even smaller, therefore I get to ignore them. Epsilon dot squared can also be ignored. Epsilon being small, epsilon dot is also small, so epsilon dot squared is also very small, it can be ignored. So ignoring epsilon dot squared, this is what I'm left with. How do we move ahead from here? The idea is to isolate terms containing epsilon. Now here there is an epsilon, there is an epsilon dot. I want to isolate terms that contain epsilon. So what I can do for this term only, integration of x dot epsilon dot, is that I can use integration by parts. And the formula that I am going to use, I'll write down the formula for integration by parts here. Integration of ft dg dt, g is a function of time, I'm not explicitly writing it out, dt from t1 to t2 is ft times gt, the limits being t1 and t2, minus integration. The second term is very easy to remember. You just flip f and g. So what you get is gt times df dt integrated in time between the points t1 and t2. So this is the formula for integration by parts that I'm going to use. Let me calculate integration x dot epsilon dot dt right here. Right. If I compare this with this, what is my f? Let me write down my f here. F is, I think it's simply x dot, and dg by dt is epsilon dot, which means g is epsilon. So I know what my f and g is. So using this formula, I can now write f times g, which means x dot times epsilon evaluated between t1 and t2 minus integration g df dt. G is epsilon, df dt. F itself is x dot. Another derivative of x dot with respect to time will give me x double dot, which means x has been differentiated twice with respect to time, dt from t1 to t2. Now I know that epsilon evaluated at t1 equals epsilon evaluated at t2, and they are both equal to 0. So this term goes to 0. What I am left with is minus integration epsilon times x double dot dt evaluated between t1 and t2. The integral goes from t1 and t2. So in place of this, I can substitute this. I'll need this formula. So let me erase whatever comes in between. This is only for x dot epsilon dot. Let me isolate all terms. Let me write out all terms individually. Integration from t1 to t2, notice there's The first term is half mx dot squared dt. So it's half mx dot squared dt. The second term, half cancels to x dot epsilon dot dt, but x dot epsilon dot is this. Integration of x dot epsilon dot is this. So I get a minus sign outside. The limits are of course t1 and t2. I also get an m. So there's an m epsilon times x double dot dt. What I've done is I've written out this term. I first multiplied half m with this, and then I've used the whatever I got after I integrated this using integration by parts, which is this. I substituted it. So these are the two terms which come from here. The next term is minus integration Vx dt minus integration epsilon dv dx dt, and all integrals are from time t1 to time t2. Okay, now let me start grouping terms. Let me group this with this, and let me group these two together. So I'm already out of space. Well, let me write it down below. What I get if I group these two terms, I think I'll jump a few steps now. If I group these two terms, I get the action half mx dot squared minus vx all integrated in time dt gives me s. So this term grouped with this term gives me back the action s, and what I'm left with is minus epsilon integration mx double dot plus dv by dx dt. So I get back my original action plus something extra. Why did I get something extra back? Because the path for which I calculated my action wasn't the correct path. It was the path which, in trying to figure out the correct path, I had missed the correct path by a quantity epsilon. So I can write it as action plus the variation of action. If the path has to be the correct path, the variation in action has to be 0, which means this quantity, this term has to be 0. So if I continue here, notice what I said. I said that I got back my original action plus something extra. Well, I got back my extra because my x wasn't x. My x had been shifted. It had been shifted by an amount epsilon. And I had missed my correct path by an amount epsilon. So I got back my original action plus something extra, which is the variance or the variation in action. And if my path has to be the correct path, the variation in action has to be 0, which means this quantity has to be 0. If this quantity has to be 0, it means that integration mx double dot plus dv by dx all integrated in time has to be 0. I've taken the epsilon that was out of the integration sign, I've taken it to the right hand side, and 0 by epsilon still gives me 0 on the right hand side. Now, if this integral has to be 0 for any two arbitrary times, the only thing that is possible is that the integrand is 0. The integrand is 0. If I equate this to 0, I get mx double dot equals to minus dv by dx. And I hope you know that minus dv by dx is the force. It is the conservative force. So I have derived Newton's second law starting from the principle of action. Well, we'll leave it at this.